our next speaker is Julia Silge from RStudio, and she'll be talking to us about data visualization practices for real-world machine learning. So Julia, really happy to have you here, and the stage is yours.
Great. Thank you so much. Thank you so much to the organizers of this conference for getting all of this going, and to the sponsors. I'm really excited to be here talking about data visualization today. I was looking through the schedule. Day one was so fantastic of this conference. This is my first time to be at this conference here, and day two looks really interesting to me. And there are actually quite a number of talks today that focus on data visualization. A lot of people use R, turn to R first because of the data visualization abilities that it has. And data visualization, like plotting, graphing, is such an important part of the process for all data practitioners. It is also a really important part of machine learning, and that's what I'm going to focus on here. It is a huge part of our process of communication outward when we have some analysis or model that we have built, that we have completed, and it's time for us to communicate about the results. But what I'm going to be talking about today is something somewhat different. It is about how modeling practitioners use data visualization to make better modeling choices, and how plotting and graphing is a tool of the system designers and operators themselves. So a lot of what we're going to be talking about today is true because data visualization is so effective at surfacing information to human beings. When it comes to data, these visual ways of perceiving information form how we think about the work that we're doing, how we understand the problems that we're solving, these models that we're building, and how we decide. I especially want to focus on data visualization as a support and an aid for decision making. And it's because building models or machine learning systems is a complicated, involved task. And I want to explicitly frame these plots and graphs that we make the way Tamara Munzner does here. So we use our computer-based systems, our code here, to represent our data sets for a specific purpose when we're building models. And it's to help us carry out this task more effectively. We're building the plots to help us carry out the task of building models more effectively. And when it comes to models and machine learning, being more effective, like building better models, can have a couple of different meanings. It can mean more accurate. It can mean more practically appropriate for whatever situation we're working in, and it can mean more fair. We're going to talk about all of these during this talk. So I work on an open source framework in R for modeling and machine learning called Tidy Models, and a lot of the examples that I'll be showing today use Tidy Models code. Some of the specific goals of the Tidy Models project are to provide a consistent, flexible framework for real-world modeling practitioners, whether you're just starting out with modeling or you are a very experienced modeling practitioner, to harmonize the heterogeneous interfaces that we find in the modeling world R, and to encourage good statistical practice. And I'm really glad to get to show some of what I'm working on and building along with my teammates. But a lot of what I'm going to talk about today isn't specific to Tidy Models, and in fact isn't specific to R. So if you are largely an R practitioner, but sometimes use Python or another tool for modeling or machine learning, a lot of what we're going to be talking about today applies. We're focusing on something a little bit bigger picture, which is these data visualization practices for real world folks engaged in building models. And I want to start by asking this question: when do modeling practitioners build data visualizations? So asking this question requires us to think about the process of model building and to build a mental model of model building, if you will. So I want to put this out there as a schematic of what might happen during a typical modeling process. So if we start from the point when, say, you or me as like a modeling practitioner first sees some new data and to the point of having a working model. So the model process starts with exploratory data analysis, or EDA. And this is the systematic, iterative process of exploring data to investigate it. After this comes feature engineering. This is the task of taking the original variables that we have and transforming them to more useful features, more useful variables for our modeling purposes. Then after this comes model fitting and tuning. I have represented this here with lots of little skinny bars to communicate that when we use best practices here, we often use resampled data sets. And so we fit and tune and fit and tune and fit and tune. And typically during a model, during a typical like model analysis, we aren't just, we don't go in knowing what kind of model we want to use or that is going to work best. But in fact, we need to try out multiple different kinds of models because we need to know which kind. We need to empirically test out which is going to work. At this point, comes model evaluation. This is when we measure how well each of these models performs using some metric that's appropriate to the specific kind of model that we are, models that we're trying and the kind of problem that we're working on. Notice, however, though, that we're not done at that point because this process is iterative. We go back and we do EDA again. We do feature engineering again. We use what we've learned during the process to go back, do a better job. Try out the models that perform best with the new information that we've gained, and then keep going. Notice that we're heading towards some goal. The process is going to end with some goal or output. This might be communicating the results to some stakeholders, or maybe deploying the model to some kind of production system, like an API or something. I've represented this as a skinny bar here, but really that's transitioning to a whole other set of tasks. So in this talk, I'm going to focus on really everything before that, this iterative process of building the model itself. So machine learning practitioners can, of course, make plots at any point during this process, but I want to make the argument that there are two phases of the modeling process where practitioners use data visualization the most. And the first of those is exploratory data analysis. I said before, the EDA is this iterative phase of investigation, question generation, and then refinement and exploring. So some people might think this phase is, outside of model building, but we're going to see how, what happens during this process has a huge impact on models. The second phase, where people build a lot of models, or build a lot of plots, is model evaluation. So this is the part of the modeling process where a practitioner has trained probably multiple models and is assessing, measuring, and comparing how well these models have performed. So if you were able to come and look over the shoulder of a modeling practitioner as they went from the beginning to the end, these would be the two phases where you saw that person building the most plots and graphs. And in my opinion, building a lot of plots and graphs during these two phases is a sign of a healthy model building process. The reason why is because these are the points of the most important human decisions. These are decisions where validation of them can sometimes be difficult. Often we might say that there's art, not science involved, and that's because it's full of trade-offs. Priorities are having to be weighed, and one priority may have to be weighed down in favor of another. And visualization is being used as an aid or support to carry out these tasks, these human tasks, more effectively, just in the way that Tamara Munzner described. So let's dig deeper and learn more and start with EDA. Let's ask this question: why are these plots built? So at a very high level, these plots are built to understand the data. When a practitioner starts out on a modeling project, this is one of these first substantive tasks being faced. And the reason that we as practitioners need to have this understanding of the data is because there's about to be a whole bunch of decisions being made. These data visualizations let practitioners ask and then refine specific questions about the modeling goal, like what kind of model is appropriate. This then feeds into the feature engineering phase and answering the question, what kind of modeling pre-processing is needed? And all these kinds of questions are ones that machine learning practitioners, modeling practitioners ask, refine, and answer by making plots during EDA. So let's look at a couple and see what it is that we're talking about. So some of these plots take the form of very familiar statistical graphics, like this scatter plot. So this plot uses a data set called the Palmer penguins. It's a data set of penguins observed in Antarctica near Palmer Station, and it maps each observation to a point on the plot with aesthetics like the positions, X and Y, size and color, representing things that have been measured about these penguins. Exploratory graphics like this are important for machine learning practitioners because well, for starters, they help us understand the type and amount of data that we have. And then going further than that, they highlight the relationships in the data that we can use in feature engineering or models. So if we wanted to build a classification model to predict the species of the penguins or maybe the sex of the penguins based on the other measurements we have, the relationships that we discover in this kind of graph inform the steps that we would take moving forward. Plots for EDA don't always look like such super classic statistical graphics. So in some ways, this plot is just a scatter plot, but what's being mapped is different. Well, it's a map. So what it's showing here is a data set of trees in San Francisco, and that big area, empty area, is Golden Gate Park, and those other sort of empty areas are smaller parks. And so right away we've learned something. The trees in the parks are not in the data set. The color is mapped into who is in charge of maintaining each tree, either the Department of Public Works or someone else. So if our goal would be to train a model to predict the maintainer of the trees, a plot like this one holds so much information for the practitioner, the person training the model, in terms of what kind of model might we try, what predictors do we expect to be important, and we learn all this just from using visualization as a tool in the process. And so machine learning practitioners use visualization during EDA to make many, many different kinds of plots. So it's important that the tools we use during this phase facilitate this kind of like fluent iteration through lots of kinds of graphs. I have personal experience with decades of various scientific plotting tools, and I think that learning about and internalizing the concept of the grammar of graphics is a huge step in getting better at this kind of fluent, efficient iteration. And that adopting a system that applies this grammar just gets you a huge step forward in this kind of efficiency in asking, refining, and answering questions to get ready to train models. So ggplot2 is arguably the best known system that implements this grammar of graphics. And the plots made here in this talk are all plots that I've made myself using ggplot2. One of these first questions that I've already said that we ask and answer in this process is what kind of model is appropriate? So let's start with like just a really straightforward model that we might want to start with. Linear regression using ordinary least squares. In tidy models, One of our goals is to harmonize the heterogeneous interfaces that we often find in like the Wild West of R's modeling ecosystem. So we separate out the kind of model we want to train, linear regression here, with the computational engine we want to use here, which is LM, meaning like basic ordinary least squares. So let's say during EDA, I discovered that there's many predictors, just a ton. So many that I'm worried about overfitting using some approaches. So I could use the fact that I knew about the large number of predictors to decide to try a regularized model. So in tidy models, I can fluently switch back and forth and say, hey, try regularization by switching out the engine. For some other modeling problem, I might see that during EDA, there's a lot of complex interaction between variables. And then I could choose a different model, like not a linear model, just a different model entirely. So tree-based models, like random forest models, are good at learning interactions between variables. So the trees in San Francisco that's a data set where I might decide to do that. There were more variables in that data set than just the spatial information, but we could see just from that initial map that there were complex relationships that were related to the outcome. And if you remember, that outcome was not continuous, but was a label or categorical variable. So we need to build a classification model rather than a regression model. And again, in tidy models, this is something that we can switch fluently. This might be just the most basic thing that we can start with, but even this is something that practitioners learn from EDA, often through visualization. What kind of model is appropriate? The next thing that we often move on to is feature engineering. In tidy models, we capture data preprocessing and feature engineering in the concept of a preprocessing recipe that has steps. So as this illustration shows, you define the steps, you prepare them using some training data, and then you apply them to any data set, like testing data or new data. So the specific feature engineering steps are typically things that we decide to do because of what we learned during EDA. So this example data set is of houses in Ames, Iowa. So we have a lot of information about the house characteristics, like how big they are, where they're located in the city, and their last selling price. So this plot shows that sale price on the y-axis and then the latitude on the x-axis. So there's a big hole there. That's where Iowa State University is. And then there's some unique and complex structure and price as you move across the city. So we have a lot of options. If we decide like how we might try to model that structure to be able to make a good prediction. But one option we have would be to use splines to build new features for modeling. So to do feature engineering with splines. The thing is though, we'd have to decide how many spline terms to use. 2 doesn't look like it captures the real structure very well. 5 looks better. I would believe 10. 20 seems okay, but I'm starting to feel a little skeptical. Oh, at 50, I no longer believe this. And at 100, this is just silly. So what's great about data visualization during the process of EDA is that we as machine learning practitioners can see and absorb this and then use it to make decisions. If you use tidy models, these decisions may end up looking like this, with a feature engineering recipe that is defined with steps that transform and prepare our data to get it ready for modeling, whether that's dealing with the factor levels or creating indicator variables, or, as shown here, setting those 10 spline terms in that last line. So whether it's engineering new features, choosing an appropriate model, or understanding data quality, data visualization during EDA has a huge impact on what modeling practitioners do later on. And so in a lot of ways, it's the foundation on which the rest of the model process is built. So it is possible a lot of times to estimate the best answer or value or option for some of these choices we've talked about. Like we could tune the number of spline terms using our data, but it is nearly impossible to remove entirely the element of human judgment from those choices. Or at least it's a bad idea. Machine learning algorithms are astounding. They're incredibly capable of learning patterns from large amounts of data. So vigorously adopting EDA and data visualization as part of the modeling process is a safeguard that we have against ending up in a situation where you have to ask yourself whether it was a good idea to just deep fry your data. So now let's move on and talk about model evaluation, that phase where we have trained and possibly tuned models, and we have predictions to compare to true values, and we can assess how our models are performing. Let's again ask this question: why are these models built? So at a very high level, why are these plots built? So at a very high level, these plots are built to understand the models. And here we're assessing performance. This is the point at which we as model practitioners have to reckon with questions about success and failure. And often we're trying out several different kinds of models, and we have to we want to know which one performed best. This also allows us to interrogate subgroups, and this is typically where discussions of model fairness comes in. A lot of the current work on machine learning bias and fairness focuses on how models perform differently for different subgroups, maybe for different legally protected classes that may not have been included directly in the model as predictors, but we may find at the end that we see different results for these groups because maybe some of the things we are using as predictors are proxies for those. Model evaluation is also concerned with understanding why a model is making the predictions it does. And for all of these questions, practitioners heavily use data visualization for a lot of the same reasons that it's used during EDA, which are largely the same reasons that anyone ever uses visualization. These plots that are used to ask and answer questions to show relationships clearly that would be difficult to see otherwise. And there are these supports and aids for decisions that need to be made. Here, the decisions are which model should I use? Is this model fair enough? At the same time, there are some pretty unique things about these plots that I think are interesting to discuss. One of these is that a lot of the plots used for model evaluation involve graphical norms or idioms. So this plot shows two model evaluation metrics for a lasso regression model and how they change with the regularization penalty, like how regularized it is. So someone who's familiar with these kind of models can look at this plot and quickly recognize whether or not it worked, whether or not it's a model that needed a lot of regularization or a little bit. And maybe looking at the R squared there, how well, or in this case, how not well, the model fit the data. So this is like a shorthand for, or an idiom that packs a lot of information for a very familiar audience. This plot is similar. It is a receiver operator characteristic curve. It's 10 of them actually, for a model trained on that Palmer penguin data that we discussed at the beginning. And it's a visual representation of how well a binary classification model is doing. So the more up in that left-hand corner the curves are, the better the model is doing. So these axes have the true positive rate and the false positive rate on them. And ideally, we want both of those to be great. We want a model to be able to do a good job at both of those. This is another example of a model evaluation visual idiom that's familiar to modeling practitioners, and it can be used to compare models, to assess a model, and so forth. So these kinds of visual idioms are a great fit for automatic plotting methods. So when we talked about EDA, I highlighted the need for a really flexible plotting framework that can be used to create any kind of plot really fluently. And we should, adopt the grammar of graphics to let yourself be able to create anything you want in a really flexible way. A lot of model evaluation plots are the same every single time, and practitioners can be better served using shortcuts built by tool builders like my teammates and me, because it can be a hassle to copy and paste the code for an ROC curve every single time. However, not all plots for model evaluation are these kind of standard idioms that are considered normal and typical in the community. This is also a model evaluation plot. It's for a model predicting the class of a volcano, and each hexagon shows the percent of volcanoes that have been classified correctly within that little area on the Earth. So while knowing about some key automatic plotting methods are a useful part of the visualization toolkit for a machine learning practitioner, still having that fluency and a flexible visualization system is very important. There's not always going to be an automatic plotting method or one of these idioms to visualize model performance in the way that you need to. So far in model evaluation, I've focused on plots that talk about how models are performing in terms of a metric like RMSE or accuracy, but and some current work on fairness falls into that category. But model evaluation activities can also encompass model explanation. And visualization is also a key tool for explaining models. Model explanation falls into two main categories. The first are global explanations, where we evaluate what features are important in a model's predictions overall. So this plot is from the San Francisco trees example again, and the height or the length of the bars correspond to how important that feature is in predicting whether the tree is maintained by the Department of Public Works or not for a random forest model. So having a private caretaker is the most important in predicting that, yes or no, and the spatial information are the next most important. So the other kind of main kind of model explanation the other main kind of feature importance here is at the individual observation level. So this is also called local feature importance. So there's multiple ways to do this. This particular plot shows an example of a Shapley additive explanation for a passenger on the Titanic and a model predicting whether or not he would survive. So the Shapley value is the average contribution of a feature to the prediction in different combinations or coalitions for this model. So the box plots show the distributions of those values and all those different coalitions, and the bars show the average. But just for that individual, not for the model overall, just for that one person. And for both global and observation level model explanations, these plots are used by the creators of these machine learning systems to evaluate and to understand them. And at this stage of the modeling process, we are again at a point of important human decision. And model explanation, together with model performance, can be used to make these choices. Through this whole exploration of data visualization and this machine learning process, I focused on plots made by system designers and operators for themselves as a tool to make better modeling choices. So these are plots made by practitioners for practitioners. So often when we talk about data visualization, we center it as a communication tool. And it 100% is, but in this case, we can explore some of visualization's other functions, like its ability to be used by system designers to understand that system more fully. I've been interested to see, maybe over the past year or so, parts of the machine learning community explore what are called participatory approaches to machine learning, where system designers purposefully partner with people who are impacted by the system, like the users of the system, in shaping or designing the system that they're building. And I think this is going to be interesting to watch, like the broader statistics, modeling, machine learning community start to think through these ideas, because that kind of practice and approach is going to have to impact choices all through that process that, I showed that schematic for, including what kind of plots to make. Because it might change the answer to this question. Who are these plots for? What I don't think it will change is the main purpose for any given data visualization. Some plots are created to help us understand the data that we start with. This is the input for the models that we create. So investing in data visualization to understand data is like laying a strong foundation. And some plots are created to help us understand the models that we are creating, the output. And so careful visualization practices in model evaluation sets us up for success in models that are as accurate, as appropriate, and as reliable as possible. And with that, I'll say thank you very much. I want to be sure to thank my teammates on the Tidy Models team, as well as the folks who organized the Tidy Tuesday project. So Tidy Tuesday is a weekly social data project, and most of the data sets that I shared today are from that project. So I'll say thank you so much, and we can see if there were some questions to answer.
Thank you, Julia. That was really a great talk, and you've got a lot of compliments going on in the chat. And we do have a couple of questions. So the first one comes from Alice, who's asking, where do you get the ideas to use non-standard plots for model evaluation?
That's a great question. So I think that, so most of the time, this comes from the structure that is in the data. So, and it often feeds out of whatever was learned during that EDA process. So if there is, so the example that I showed was a map. And so when there was spatial information, that's often really important to see. But often other data sets have analogous kind of structure where you want to understand something that would be analogous to the spatial information in that. If we kind of lay that strong foundation in the EDA process where we see whether it's a data set of people, and we see, I see that we have these different groups of people, and then I want to make sure I understand how performance changes over these different groups of people, or spatially, or often that information comes out of what we know about the structure of the data, and that is usually learned during EDA. And so that kind of begs the question, how do you get better at EDA? How do you learn what to do during EDA? And that's something that I don't know that we have a really good answer to. There are, so I certainly, if we talk to people about this, we say things like practice, we say things like watching other people. We say things like being able to see what is it that other people do. We say things like experience. And I think this is actually a really open, interesting research question. How do people get better at exploratory data analysis? What are the skills that push people to get better, other than just sort of blanket statements around practice? Or so I think that's a little bit of an open question.
Yeah, no, thank you, Julia. That's a great answer. And, I don't know how many people are actually, kind of diving into that research question, but indeed, it's the one that is important, right? A couple more questions. I think we have a few more minutes until the break. So another question comes from Manuel, who is asking, how efficient are the packages with big data sets, say more than 10K?
Yeah. So if you're talking specifically about tidy models, so if you're talking about, for example, the issues of resampling and making taking your data set, being able to make resample data sets, that has been designed to be very efficient, allow you to very efficiently resample your data set and be memory efficient in that way. If you're talking about the modeling aspect, the tidy models is an interface to modeling functions in R, and some of them are better and worse for different size data sets. At the size of 10K, I don't think you're going to run into a lot of problems for most of those, and especially for things like regularized regression problems or random forests. I think you probably will be doing okay. If you start to running into bigger data, then we do currently have support for things like modeling in Spark and whatnot. So we are interested in looking at what are people doing and how can we support some of these different options that are out there for what you might call bigger data, not in-memory data.
All right, thank you, Julia. Maybe we can take one last question. So it comes from Mike Smith, and the question is, how do new practitioners learn what the standard idioms of those plots are?
That's a great question. That is a really good question. So So I think that the ways that I have learned what some of those idioms are through the ways that through experience with working with more like this. So this question of like, how do people learn the new things? How do we get used to the new things? I think through working with more experienced people, I think through explicit teaching, I think through good teaching materials. I think that I was talking to one of my coworkers, Mina Sedenchaya Rendell, about this, and because apparently there's been research done about the like the QQ plots and how like they're like kind of pointless because like even experienced practitioners look at them and like don't know how to interpret them very well. That they're basically not very helpful because either they don't show a problem, or if there is a problem, like people don't know what to do about it. I don't know. It's not really my area of expertise, but we were contrasting that with some of these things like an ROC curve, that are helpful, that people do gain things from, like, oh, this did work or this didn't work. And so I think careful people who are in the position of mentoring, teaching, even less formal mentoring, kind of learning to explicitly call out when something is unique versus, hey, we do this all the time, let's notice this. So starting to have starting to like mentally kind of call those out and have that be, and having people who are in the teaching positions having more knowledge and awareness about which of these kinds of idioms have been shown or have the sort of community like, actually, yeah, this one does work. These kinds of things are part of the literature community / best practice, because they are helpful to people, versus ones that like, why hold on to something that research and or practice has not shown to be as useful. So that was a little rambly. Let me sum up. I think through formal and informal mentoring and teaching, and I think that this can be improved by the people who are on the mentoring side being a little more deliberate in the choices they make.
Okay, thank you so much, Julia. One more time, I have an opportunity to clap. I saw a lot of claps in the chat. I'll just voice that since I have a mic on. But some of the words that people are saying, amazing, engaged, and insightful, I can only echo this. So thank you so much for giving a presentation and for having such a lovely Q&A.
Thank you so much for having me.
Thank you, Julia.